Uh, Welcome to video on operational amplifiers. Uh, Before we start the basics of these operational amplifiers, let us go through some prerequisites. Okay, if you are knowing Ohm's law, KVL, KCL, and basics of amplifiers, so this video will be very useful. These are some preliminary things. Okay, with this introductory remarks, so let us start the op-amp introduction. So now this is the symbol of an op-amp. So it has got two inputs, plus and minus, and there is an output. So if I call this as Vi, this is V plus. So where this negative indicates, so this negative indicates it's an inverting input. So this negative is actually indicating it's a inverting input terminal. It's a negative inverting input terminal. So you have a plus also. This indicates it's a non-inverting input terminal. So this is input terminal, and this is the output. So if I write it as V naught, so V naught is the output. V naught is the output. So basically you have two inputs and a single output. So this is a single output. So then how does this V naught is related to these two? So this V naught is related to these two with, so this is A naught times V plus minus of V minus. So this A naught is referred as open loop gain of the op amp. This is open loop gain of the op amp. When I say gain, it is voltage gain. So this is open loop voltage gain. So now this is A naught, and what is this output voltage? Output voltage is open loop gains the difference of the two inputs, Of course, we know that this is an electronic circuit, need to be supported with a supply voltage which is plus VCC and minus VCC. So this is, there are two supplies required for this. It is plus VCC and minus VCC. So plus or minus VCCs are the supply voltages. Now this A naught, typically this A naught value, which is the open loop gain, which will be in the order of 10 power 4 to 10 power 8 is the ratio or the voltage gain of this. So this is specified in terms of, so now I can specify this in terms of dB as 20 log of 10 power 4 to 20 log of 10 power 8. So this is a typical gain of the amplifier in terms of dBs. So as you can see, this, okay, we know that 20 log of 10 power 4, 10 power, so this is 20 log of 10 power 4 would be 80 dB. So this is 80 dB, and this can go up to 120 dB. So 20 log of, so this is 160 dBs. So this is the gain, which is, of course, even it can start from 40 dB also. The range can be 40 dB to 160 dB. This is the open loop gain of the op amp. So in most of the cases, op amp will not be used in this open loop mode. It will be put in the closed loop gain. So when I say closed loop, so this output, a portion of the output will be fed back to input. So we will write two very interesting or very basic circuit diagrams of the op amp. One is called as inverting amplifier, which is based on op amps. So we'll take the op amp. This is minus plus. So now to this output is connected back to input using these two feedback resistors. These two resistors are used as feedback network. This is R1. You can see this is going to inverting terminal, so this is called as negative feedback. Negative feedback is done. Of course, since it is inverting amplifier, here I am applying the input voltage. Input is applied here itself, and this will be grounded. This will be grounded. Now we need to find an expression for V0. What is the expression of V0? So here I am applying the input. So let us write this current as I1, this current as IF, and you can consider this current as some IX. So this is the node A. This is the node A. So by writing KCL at node A, we know that current entering the node is equal to current leaving the node. What is the current entering the node? It is I1. These are the two currents which are leaving. I1 is nothing but IX plus IF. So this is a current entering, and these two are the currents leaving this node. So we know that the op amp has got an input impedance of infinite, so this current is 0. So then ideally, considering this op amp as an ideal amplifier, the input impedance is infinite. When the input impedance is infinite, we know that there is no current flowing inside it, so it is 0. So I1 is equal to IF. I1 is equal to IF. What is this I1? We know that I1 is the current flowing through resistor R1. So we know that when you have a resistor, if there is a voltage Vx and if there is a voltage Vy and if the resistance is some Ra, then what is the current flowing through this as if you assume it as Ia? Since you are assuming the current direction to be going from here to here, Ia will be given by potential difference across these two, that is higher potential. You are treating this as this is higher potential, actually it is Vx minus Vy by the resistance of that resistor. So current flowing through a resistor is nothing but potential difference, that is higher potential to lower potential, divided by Ra. Why you are considering this as higher potential? That's what we have assumed. You can assume it as this as higher potential by writing the direction this way. Using this, I can find what is expression for I1. So you know that this is I1. It is a potential difference across this resistor divided by the resistance. Now we know that at this point I have a potential V in. What is the potential at this point? Since you can see this is grounded, for an ideal op amp, there is something like called as virtual ground. This is virtual ground. So virtual ground actually indicates there will be no potential difference between this and this. So there will be no potential difference between these two. That is, whatever is the voltage that is there at the non-inverting terminal, same will be available at the inverting terminal. So what is the voltage at non-inverting terminal now? V plus is 0. When the voltage at V plus is 0, naturally you're going to have the same voltage at V minus. So V minus is also 0. So you're going to have 0 volts here. When it is 0 volts, is the voltage 0 here again? Because these two are same point. So then what is I1? I1 I can write it as, it is V in minus 0 divided by R1. So this is I1. What is IF? The current IF that is flowing here is this potential minus this potential divided by this. What is this potential? That is 0. What is this potential? Here, the potential here you assume to be V0, because this is V0, divided by RF. So use the expression of I1 and IF in this KCL expression and try to obtain. So do you have V in by R1 is equal to minus of V0 by RF as the equivalent of this. So now I can write V0 by V in as equal to minus RF by R1. or I can write V naught is equal to minus RF by R1 times Vin. So the output voltage is minus RF by R1 times the Vin. So now depending on the values of RF and R1, you can get the output voltage compared to input voltage multiplied by this value. So the gain of the amplifier, this is voltage gain. Voltage gain of the amplifier after making this R1 and RF connection is given by V0 by Vin is equal to minus RF by R1. This minus indicates that it is in out of phase with the input signal. Suppose you want to find out what is the meaning of this. Suppose if I have this is minus, this is plus. If I have it as 1 kilo ohm, if I have this as 2 kilo ohm, and if I write this is V0 and this is grounded, if I apply a sine wave of 1 volt, assume that I'll apply a sine wave of 1 volt. This is now 1 volt and this is minus 1 volt. This is with respect to time. If this is Vin, how does your V0 looks like? V0 looks like, again it's a sine wave, but since what is AV? AV is equal to, this is, you name it as RF, this as R1. So now is it not minus RF by R1 is the gain, which is nothing but minus 2k by 1k. This kk will go off. Do I have a gain of minus 2? AV is minus 2. So what is this minus 2 indicating? Output voltage is twice of the input but in out of phase. You can see input is increasing but the output will be going reducing. Here this is how the output comes. So now this is minus 2 volt, this is plus 2 volt. So this is again with respect to time. So this is what we mean by out of phase. So this can be 200 ohm also. If it is 200 ohm, so assume that I'll replace it by 0.2 kilo ohm. So when it is 0.2 kilo ohm, what you have is 0.2 k by 1k, kk will go off, you have 0.2, 0.2 by 1 is 0.2. So then in such case, of course it is minus 0.2. So then the output will be here, it's going like this. It is still out of phase, but the amplitude is minus 0.2. Minus 0.2, it will go up to 0.2. This is the voltage. So now here the AV magnitude can be greater than 1, AV magnitude can be less than 1, depending on the ratio of, this is greater than when RF is greater than R1, if this RF is less than R1. So then AV magnitude is less than, as we saw here. This can be 2 or this can be 0.2. Fine. This is about inverting amplifier. You will see its counterpart, non-inverting amplifier. This is inverting amplifier. So for this, it looks like this. Again the op-amp minus plus. Now the input is applied to non-inverting amplifier. So this is Vin. Now again it is the same resistors R1 and RF connected between output and inverting terminal, and this is now grounded. So this is again R1 RF V. So this is V0. So again now we need to find the expression for V0. We need to find what is V0. So for that, let us again assume a current I1, a current IF, and this is current 0, because we know that this current is 0. So this is Vin, means because of virtual ground this voltage is also Vin. This voltage is also Vin. So then what is I1 expression? So I1, I can write it as, of course, KCL at this point. KCL at this point is I1 is equal to IF. I1 is equal to IF plus 0. Plus 0, considering this current as 0. So then this 0, you can take it out. What is I1? It is 0 minus Vn. This voltage is Vn. Of course, this current is 0. So this voltage is Vn. 0 minus V in, because it is a potential difference across resistor, because you are treating this as higher potential because your assumed direction is like this. When your assumed direction like this, so this is at higher potential than this. So this is 0 minus of V in. So minus of V in divided by R1 is I1. What is IF? IF is nothing but this voltage is V in, this voltage is V naught. So it is V in minus V naught by RF. So I can write minus V in by R1 is equal to V in minus V naught by RF. So can we rewrite this as minus V in by R1 equals V in by RF minus V naught by RF. I can put this onto the side, then this will become minus V in by R1 minus V in by RF is equal to minus V naught by RF. So I can take minus sign here, minus sign is also here, also there. I can take V in outside, and of course I can take minus V in outside and write it as 1 over R1 plus 1 over RF is equal to minus V naught by RF. So this minus and minus will go off, and can I write now? So V naught by RF is equal to V in into 1 over R1 plus 1 over RF. Now I can write V naught is equal to V in. You multiply this RF here. Is it not RF by R1 plus RF by RF? Now this will go off. So can I now write V naught is equal to V in into 1 plus RF by R1? This is the expression for output voltage. This is the expression for the output voltage in terms of V in and RF and R1. So you can see there is no sign here. There is no negative sign. So that's why it is called as non-inverting amplifier. So what is the gain of the amplifier? It is V naught by V in. AV is equal to V naught by V in is equal to 1 plus RF by R1. This is the expression for voltage gain of non-inverting amplifier. It's very simple. We assumed a current I1 flowing like this, IF flowing like this. This current is 0 because it's a high input impedance. So then we wrote the KCL at node A. This is node A. Current entering the current is equal to current leaving the current. That is this. Then we wrote the expression for I1, which is nothing but this voltage minus this voltage by R1. That is 0 minus V in by R1. IF is 0 minus V naught. Sorry, this is not 0. This current is 0. This is I. So what is the voltage here? It is V in. So it is V in minus V naught by RF. Then simplifying this, you'll end up with this as the expression for the output voltage and the voltage gain. So we will find what is the output voltage of a particular example. Let me take it as plus here. This is minus. So this is a non-inverting amplifier. I will do this. This is now grounded. This is R1. Let us do it. Take it as 2 kilo ohm. So let us take it as 4.7 kilo ohm. This is RF, and this is, let us assume it as 0.5 volt as V in. We are supposed to find what is V naught. So what is V naught now? It is nothing but V in 1 plus RF by R1. RF by R1. So what is V in? It is 0.5 volt. It is 1 plus RF is 4.7 K, and this is 2 kilo ohm. So now what is 4.7 divided by 2 plus 1? It is 0.5 into 3.35 into 0.5. Can you see output voltage is 1.675 volt? If you apply 0.5 volt a DC voltage, even you can apply DC voltage and you'll get a positive voltage. Suppose if you apply sine wave, now let us assume that for the same circuit, if I am applying a sine wave of 1 volt, if I am applying a sine wave of 1 volt, this is 1 volt. So now this is V in with respect to time. So how does your V out will look like? So now you can write, you can put the reference here. This is V naught, this is 0, 0 here. Since input is 1 volt and gain is 3.35 for the same what ratio of RF and R1, does your output goes in the same direction with an amplitude 3.35 times the input. So what will be this? It is 3.35 volt. This is minus 3.35 volt. This is again with respect to time. This is what is the output waveform if the input is a sine wave 1 volt signal. You can see it is now amplified by this times because this is nothing but 1 plus RF by R. Correct? So it is also possible to have something like this. Suppose you have, instead of only one input, assume that this is V1 and this is V2. Assume that V1 is 1 volt and V2 is zero point 0.2 volt. Let us assume this as R1 is equal to 1 kilo ohm. Let us assume R2 is equal to some 3 kilo ohm. Let us assume RF as this is minus, this is plus, this plus is grounded, and let us consider RF as 10 kilo ohm. 10 kilo. So what is V naught now? Now V naught is due to both the inputs. So now V naught can be written as minus of RF by R1 into V1. This is 1 voltage plus of minus of RF by R2 into V2. You can see you have to consider this voltage as well as this voltage for getting the overall voltage. So what is this now? It is minus 10k by 1k into 1 volt plus of minus of 10k by 3k into 0.2 volt. So how much is this now? So anyhow this will become minus 10 plus of, so it is now 2 by 3. So is it not 0.666? This again minus. So is it not minus 10.666 volts? Because 10 by 6 is 1.66 into, sorry, 10 by 3. 10 by 3 into 0.2 is 0.666. So that is another 10. So what you have, V naught is equal to now minus. So this is like considering both inputs which are connected to inverting terminal, and what is the final voltage. There is also a possibility that you can have one input at the inverting terminal and other one at the non-inverting terminal, something like this, minus plus. This we call it as summing amplifier. Summing amplifier. So because these two are summed up here, can you see this is summed up here? Now we will see a different case where you have input applied to this as well as input applied to this. So I'm applying here as well as here. So let us consider this as 1 volt, this as 2 volt, and let us assume R1 is equal to 1k and RF is equal to some 3.3 kilo. So I want to know what is V naught. So now V naught is due to both the inputs. So first let us consider this input, let us not consider this input. If you consider only V1, is it not minus RF by R1 times V1 when you are not considering V2? Next, when you consider V2, when you make this ground V1, so it is 1 plus RF by R1 times V2. So it is, Y means this input is non-inverting input. So this will act like a non-inverting amplifier by grounding this. But that's why we know that non-inverting amplifier gain is 1 plus RF by R1. So this by this plus 1. So that's what is non-inverting gain. This is inverting in. When you don't consider this, when you consider only V1, it is minus RF by R1. So it is minus. 3.3k by 1k into 2 volts plus of, it is 1 plus, again this is what, 3.3k by 1k into how much is, this is 1 volt. So what we have now, this will go with, is it not minus 6.6 plus of, is it not 4.3 into 1? So how much is this now? So it is minus 6.6 plus of 4.3, it is minus 2.3 volt. So this, let me repeat, you have, you are applying the input to both inverting terminal as well as non-inverting terminal with a feedback. So now you have actually two output voltages, V01 plus V02. This V01 is with only V1, V2 is considered as 0. In this V02, you are considering only V2, the V1 is 0. When V1 is 0, this is, when V1 is 0, it acts like non-inverting amplifier. That my gain is 1 plus RF by R1 into V2. When you're considering only this, then you treat this as 0. Can you see V2 is 0? When you consider only this, is it not minus RF by R1 times V? Is this? We considered V1 as 2 volts, V2 as 1 volt, and we are trying to simplify this and ending with the final value of V0 as minus 2.3 volts. So this is called as a difference amplifier. This is because you are having a difference of the two. So this is difference amplifier. That's it. So we will look into few more concepts of the operation amplifier in the next video. Thank you.